In this video, we're going to talk about stress and strain and define them using our indicial notation that we've talked about earlier. And so to start out with, let's talk about the definitions of strain that we learned in mechanics of materials. Now, there are two types of strain, normal and shear. Normal strain means a change in length per unit length. And if we have a finite length, we would actually say that's the average strain over that length. But if we add to that definition and say of an infinitesimally small line segment, so in other words, it applies only at a point, that would be a definition of normal strain. Okay, shear strain represents angle change, so the change in angle in radians between, again, two infinitesimally small line segments, and originally those are perpendicular to each other. So we can use these definitions to define mathematical definitions of strain. So let's look at our coordinate system, x1, x2, and x3, and the displacements corresponding to each of those directions are u1, u2, and u3. So in other words, ui is the displacement vector here. And let's look at normal strain first. So we've got a small piece of material. It has a length along the x1 direction of delta x1, and when we stretch it, displacement is delta u1. So using that definition of change in length over original length, we can say the normal strain 1,1 is as such, and as we let the length delta x1 approach 0, then we end up with a derivative, in this case a partial derivative. So the normal strain in the one direction is the partial derivative of the displacement in the x1 direction relative to x1. Now, we're going to introduce some more notation here, which is common notation. Instead of writing out this partial derivative, we can use a shorthand method with the comma. So u1 comma 1 just means the partial of the displacement in the x1 direction with respect to that one direction. And if we have a similar expression here, ui comma ij, well, that's a second derivative. In this case, means the second derivative of the displacement in the I direction with respect to xi and xj. It's important to remember here that when you have that comma, you have repeated indices, but when they're separated by a comma there, they're not treated as dummy indices, and so there's no summation that's applied there. So using this definition, as we said, epsilon 1,1, the normal strain in the one direction, can be written as u1 comma 1, and similar for the normal strains in the other two directions, so epsilon 2,2 and epsilon 3,3 is shown there. Alright, now let's talk about shear strain. So shear strain, as we said, is angle change. And so we've got this small piece of material, delta x1, delta x2 to the sides, and there's the displaced configuration on the right. Now there are two ways we can interpret this, though. Engineering shear strain looks at the total angle change. In other words, angle 1 plus angle 2. Tensor shear strain, though, is 1/2 of that. So half of delta angle 1 plus angle 2. In other words, engineering shear strain is double tensor shear strain. So that's important to keep in mind because, again, we're going to use the tensor transformations. We have to define the shear strain as the tensor shear strain. Alright, so here's the angles, angle 1 and angle 2, and so we can show that as being the sum of angle 1 and angle 2. And we can kind of figure out what these angles are. So as we shear it in this direction, here's our deformation, which is delta u1, but the angle is going to be related to delta u1 and this side, delta x2. So again, using the nomenclature that we've set up here, angle 1 is the arctangent of delta u1 divided by delta x2. Now, because it's a small angle, with small angles we can assume that the angle in radians is approximately equal to the tangent of the angle. And so we'll say that angle 1 is approximately equal to delta u1 over delta x2. And if we let delta x2 approach 0, that becomes the partial derivative as shown here. In other words, u1 comma 2. Now we can do a similar thing to find angle 2, and we find that angle 2 is u2 comma 1. Therefore, the shear strain epsilon 1 2 is 1/2 u1 2 plus u2 1, those derivatives. And by the way, as I mentioned in just a moment, the order in which we add those doesn't make any difference, so you'll be able to see very clearly that epsilon 2 1 would be the same as epsilon 1 2. So here's our general expression for strain, and this works for both normal and shear strains. 1/2 ui comma j plus uj comma I. And you can see if it was a normal strain, those two would be the same. And so again, you'd have double those things, and the two would then cancel out. But again, that works for both normal and shear strains. And again, as we mentioned earlier, it's easy to see that epsilon ij is equal to epsilon ji. That's going to be important later on, because as we'll see when we start doing transformations, that instead of 9 independent components, there are only 6. But we can still see that this is going to be a tensor, because it is defined, strain is defined by 3 squared, or 9 numbers here. And if it then follows the transformation equation, then it's a second order tensor. Now, I've gone through that, but I'm not going to do it here. So if you want to see the proof of that, go to the end of section 1 of the class notes, and you'll see that strain is indeed a tensor. It does follow those transformation rules. Now, as far as stress goes, you probably did stress transformations in mechanics of materials. And so yeah, you can show that stress is also a second order tensor, but we're not going to do that here. So what we've established in this video is that stress and strain are second order tensors, and so using that knowledge, we'll now do the stress and strain transformations in the next video. And once we've got that established, now we're ready to actually go into some actual mechanics of composite materials into the next section.